So in the first video, I described how students investigate relationships in right triangles by building triangles on dot paper or geoboards, building the squares, and looking at the areas to see if there is a relationship. And invariably, students build something like what we see on the screen, and they discover that the area of the large square on the hypotenuse is equal to the sum of the areas of the two smaller squares, which is the heart of the Pythagorean relationship. So the question then becomes, for the purposes of this video, why do I need to incorporate CT encoding into this lesson? Well, the answer is that in some cases, students may not recognize the universality of the Pythagorean relationship. They may see it as a cool thing that happened on the triangles that they built, but that it surely doesn't apply to all right triangles. And it's kind of dangerous for them to walk away from the lesson thinking that. Okay, so in the first part of the lesson, they get a taste of the Pythagorean relationship, but we need to establish that it applies to all right triangles. And they can do that quite easily by using a code in Scratch that I have pictured here. This will be made available to them in the lesson. And here's how it works. So when I press the green flag, I am asked to choose the length for side A. So I'll just put in here 6. Okay, now what is the length of arm B? Well, I'm going to go 3. And you can see what's happening. It completes the triangle and it builds the squares on all 3 sides, but then it partitions the large square so that the student can easily determine the area. So I'll just go through that process with you. Well, I know that this area is 3 by 3, that's 9 square units. This square is 6 by 6, that's 36 square units. 36 plus 9 is 45. Taking a look at the square above here, I know I have 4 congruent triangles. What is the area of one triangle? 1, 2, 3, 4, 5, 6. 6 times 3 is 18. Divided by 2, that's 9. So each of these triangles has an area of 9 square units. 9, 18, 27, 36, plus the 9 square units in the middle, that's 45. So it's fairly easy for me to see that the relationship that I investigated on the geoboard is holding in this environment. And by just clicking the green flag again, I can investigate any number of sets of dimensions. And I will come to the same conclusion each time, that the Pythagorean relationship holds for each set of dimensions. So as students use this code, if they are thinking that perhaps it worked once but it won't work again, frequent or consistent use of this code will convince them that, hey, this relationship is true for any right triangle under the sun, and that's important. Now, could the teacher simply tell them, hey, Pythagorean relationship works for all right triangles? Absolutely. Is it as effective as students discovering this on their own and having that aha moment? It's not nearly as effective as that. So it's worth having students sit down in front of a code like this and come to that realization on their own. Okay, that'll just build a deeper understanding of the Pythagorean relationship. Now, switching topics slightly. When students engage with this code, they're not actually creating code of their own. They're using a code that has been provided for them. Yes, they're tinkering slightly because they're changing the inputs, but they're not changing the structure of the code over here, at least not yet. This is in line with the computational thinking pedagogical framework written up by Katsopoulos et al. They state that when you're bringing computational thinking and coding activities into the classroom, you can't just throw students into the metaphorical deep end. You need to bring them into it gradually. And so they suggest starting off with unplugged activities, which we did with the geoboards and the dot paper. But once the computers are introduced, they should be using or slightly tinkering with pre-made codes to kind of get used to the idea of coding and computational thinking in this environment. And once they had gained some comfort with that, they should move on to creating their own codes or remixing existing codes for different purposes. And of course, those two tasks require, or they feature rather, higher levels of rigor. Okay, so we started with the unplugged, with the geoboards and the dot paper. We've brought them into a tinkering using mode with this code, and throughout this lesson there are opportunities for students to remix this code for other purposes, and later on when they get into the Wheel of Theodorus, they are assigned the task of creating a code based on their knowledge of the wheel. So this lesson sort of runs the gamut of that computational thinking pedagogical framework, and this code being more of a user-friendly code, if you will, is a significant part of that progress.